Hello, everybody. Welcome to the Global Composite Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and the future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the Composite Design and Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. The CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together using the cloud technology. We envision CDM Hub to become the premier resources for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the global composite community. This webinar series is made possible by the support of our sponsors, including Dassault Systems, SciTech Solvay Group, and Anna Swift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org, and we will email you once the recorded video is available online. The presentation will last about 40 minutes, and we will have about 15 minutes for questions and answers after the presentation. All attendees are muted at this time. Please submit your questions through the Q&A box. After the presentation, your questions will be read and answered. And next, let me ask my colleague, Professor Dianren Zhang, to introduce our distinguished speaker today.
Welcome, everyone. My name is Dianren Zhang. I'm an assistant professor of the School of Aeronautics and Astronautics at Purdue University. It is my very great pleasure to introduce today's webinar speaker, Professor Veronique Michaud. Professor Michaud is currently Associate Professor, Head of the Laboratory for Processing of Advanced Composites, and Associate Dean of Engineering for Education at the École Polytechnique Fédérale de Lausanne in Switzerland. She graduated from Massachusetts Institute of Technology in 1991 with a PhD in materials engineering and obtained a research habilitation from IMPG in France in 1994. After a postdoc research stay at MIT, she spent 3 years at École Centrale in Paris for teaching and research in the Laboratory for Materials, Structures, and Solid Mechanics before joining EPFL in 1997. Her fields of research address fundamental aspects of composite materials processing, often including economic and environmental aspects to lower the overall product footprint, as well as the development of smart materials and structures, including self-healing, shape and vibration control, and the tailored damping. She is the author of more than 300 publications, out of which about 150 in peer-reviewed journals and several patents. She is also the co-founder of the startup Capillary Technologies SA, which was created in 2020. Now I will give it to Professor Michaud.
Thank you. So, okay. I will try to share my screen. Yeah, thank you. Okay, here it is. See if it works. Yes, it works. Okay, so thank you. and welcome and thank you all for being here today. So I will, let me just stop this. Let me also improve this. Okay, so as mentioned, and thank you for the very kind introduction. As discussed, actually, as you could see, I'm working in many different topics, but when I discussed with Professor Pipes about what I could talk about today, he encouraged me to talk about capillary effects in fiber reinforced composites, which is a topic that has been following my life from my PhD thesis 30 years ago up to now. So I think for me, it's also a travel into the past, the present, and the future of my own career at the same time as composite research. And I'm working at EPFL in the laboratory for processing of advanced composite, which I had. And let's see if this works here. I removed the title. You can see here the little red dot is where I am sitting right now as we speak, with the lake here. So capillary effects are actually you find them all over the place, and you all know about capillary effects. That's the capillary action is defined as the process whereby a fluid flows on the surface displacing air or another immiscible fluid phase that is present on that solid surface under no external force. So typically, capillary action is due to the presence of the intermolecular forces between the liquid and the solid surface. And we often see them when you use a sponge, for example, or in this example here that I will come back to. And these capillary forces play an important role in many physical systems where a fluid invades a network of narrow spaces. And I have some examples here. You have the wicking, which is taking place very often. If you have to water your plants when you're away on the trip, you could buy these wicks that are helpful. But it's also, of course, in water transport in plants. It's also in soil science. And because we're all coming out of the SARS-CoV-2 pandemic, of course, when you do this auto test, and that's a professional insight for me, you can watch the flow front of that fluid, and you can even see if there's a bit of race tracking on the side. That's what we all been watching recently, unfortunately for us. So I mentioned they're very common in soil science, and to start the talk, I decided to show you a picture which I took from a presentation. Sorry, my mouse is too fast, which is taken from a review paper that was published last year about soil science and capillary effects in soil science. And what I wanted to point out here, because we have exactly the same issues, is when you're dealing with capillary effects in porous media, you have to go across many length scales, from the molecular scale, where you have really at the interaction between the atoms, and here you have the Lennard-Jones potential, which we all teach to our first year students, and you have the molecular forces, but then you have, of course, the interaction between the solid and the liquid, and how the atoms would pack and organize, and the creation of surface tension. Then you have to go to the sub-pore scale, where you have to worry more about contact angle, but you have to worry also about the local rugosity and potential surface characteristics and roughness of your surface. And then you go to the pore scale, where you have to see what is the curvature of the pore locally, and how the fluid can interact with this. And then what we see often is what we have at the macroscopic scale, where we are working on the macroscopic system, and we have more issues of pressure, volume, thermodynamics, and macroscopic effects. And how to relate the topics at these scales is a bit difficult. We have a lot of work going on, and I will not talk much about it today, on the molecular and pore scale, on wetting, as we normally call it. But the link between this thermodynamics and geometric structure remains a little bit difficult in soil science, which has been progressing a lot over the past years, but also in composite. So I will not talk about soil science too much. I will talk about composite modeling, which is our field. And I will talk mostly about liquid composite molding, which is the process whereby you have a typically flow that is, let me just start it here, that is progressing. You see it here. And we have examples all over, actually, not only in normal composite processing like vacuum infusion and resin transfer molding that I will talk about today mostly. But also if you work on metal matrix infiltration, which was my PhD topic at MIT, or ceramic slurry, pultrusion, film stacking, pre-preg manufacturing, you always have a case where you have an infiltration process and the liquid matrix flows into a dry porous medium over maybe a fiber bundle, a few fiber bundles, or the overall length scale of your reinforcement. So we will mostly look at the flow front in our case today, because this is the location where everything takes place, where the fluid encounters the dry porous medium and where you have these capillary effects. And the main questions that I want to answer today or talk about today are these effects relevant in our composite processing world? Because the applied pressure gradient is large compared to capillary pressure values. So does it make sense to think about it? Now, if it does make sense, there are many questions. Is capillary pressure a boundary condition at the flow front, or is it something that is more diffuse that will take place over over more than the flow front? How can we observe these effects and how can we quantify them? And also, can we model them? Can we predict them? Can we anticipate their role? And you see already here, we have some examples where you see the flow front can be very sharp, but also can be very diffuse. And there it's obvious that the flow front is acting across more than just one line. So in the composite world, and as everybody knows now, we had a lot of issues to solve at first. And the first issues to solve were also how to predict, if my part will be impregnated in 10 minutes or in 3 hours or in 10 hours. And so for general kinetics, in first approximation, you don't need to look so much about capillary forces. And so they've been neglected for a long time. But there are many observations you find in literature that show that they can influence the part quality. And in particular, I will focus today on two aspects. One is the part quality in terms of void content. There's many authors, I cite here a few, Krishna Pillai, Edu Ruiz, Joël Bréard are kind of, but there are many others who have been working on this, is to define, to do plates and then look at the macro or micro void content in the plates. And then they all come up with a kind of a drawing like this that shows that there seems to be an optimal flow velocity to have zero porosity just after impregnation. But if you go too slow, so in this case, you have a very slow flow velocity, you will have a lot of porosity in your part. But if you go too fast, you will also have a lot of porosity in your part. So there seems to be some kind of magic velocity that you need to use. This magic velocity is often discussed in terms of a capillary number, which is a ratio of the flow velocity times the fluid velocity divided by the surface tension. Some people also in soil science add a cosinus theta here, which is the contact angle, but I will go back to it, that's why I don't put it. And the flow velocity is normally the filtration velocity in soil science, so it would be an overall apparent velocity. And if you keep the viscosity and the surface tension constant, of course, the capillary number really describes the velocity. If you are on the slow velocity scale, so a low capillary number, what's happening if you look at the flow in your porous medium, that is the textile you have, it's normally driven, if the system is wetting, by capillary effects. And what you have is a separation between the flow that is going faster inside the toes, where the volume fraction is high. And then if you have gaps between the toes, the flow is lagging behind. And this has been explained also that it seems that if the flow is lagging too much behind, there will be some porosity that will remain entrapped. Now, if you go on the other side and you go too fast, which is normally what we try to do if we want to go fast when we impregnate the part, you will have hydrodynamic forces that dominate. You will have the flow leading in between the toes, and behind the toes will be impregnated a bit more slowly, and you will end up with some porosity left inside here. Now, there are many questions that are linked to this explanation. First of all, what is the magic capillary number? What does it depend on? And do these porosities appear during flow? And do they remain after flow ceases? And can we actually remove them as well? So that was one aspect. the other aspect that has been becoming more and more obvious is if we do a permeability measurement, which is often useful when you do liquid composite molding, you want to know the permeability of your fabric, you do a measurement, and most of the time you can do a measurement that is a non-saturated measurement, and we will come back to this, looking at the flow front and understanding, the permeability with the model fluid from that. Some other people do saturated experiments, and many people reported a lot of differences between the saturated and unsaturated values. There's a good review paper by Capillary in 2004 discussing this also. And this is an example from Joël Bréa. And you see that, in fact, the ratio of K unsat over K sat seems to be changing, and everybody's a bit fighting between should it be higher, should it be below, should it be the same, why is it different? So I will come back to that later as well. So now, in composite processing, as compared to other branches of engineering, like soil science, we have some specificities which make our life a bit more difficult. Of course, wetting is important, but it's in competition with pressure-driven dynamic flows. So most of the cases, we are actually not talking about wetting-driven flows, but pressure-driven flows. The porous medium is really far from homogeneous. We have a strong bimodal pore size distribution, as I already hinted, with toes and spaces between the toes. And the toes can also change during impregnation. They can change shape, they can change the VF, they can compact or expand. The presence of toes orthogonal to the flow will also induce other transverse flow and potential porosity entrapment. So all this complicates our life. And just to illustrate how the typical reinforcement microstructure looks like using micro-CT, you see that you have the dark regions here that are mesopores. Between the toes, you see the toes that are here. And then if you look inside this dark region, you have micropores that are between the fibers. So the scales, you see it's 1 millimeter here. So you can have gaps that can be up to a millimeter or more sometimes, and gaps between the fibers that are in the around microns. So there's a big difference. So now, where do we start? And I will try to go from the microscopic aspects, so really the surface aspects, to the macroscopic aspects at the end. So first is to look at the surface, and we all know and studied, what happens if you put a drop of liquid onto a surface. And there is a very well-known Young's equation to describe all this. You put the liquid, it will create automatically a contact angle here, and this contact angle depends on the equilibrium of the forces created by the surface tensions of liquid, solid, and the interfacial tension between liquid and solid. And if this contact angle is below 90 degrees, the fluid is wetting the solid. And if it's above 90 degrees, the fluid is non-wetting. And these are some examples here taken from wine growing and textiles. And there are, of course, examples where you can also measure this contact angle not on the flat substrates, but also on a fiber. This is epoxy, for example, on a carbon fiber. But this is all taken at equilibrium. And this gives important data as well, but this is one data. Then we look at the capillary pressure drop. So moving from the simple substrates to a tube. And we also know that in a cylindrical tube, we can express the delta P gamma, which is this capillary pressure drop, which is driven by this the presence of the surface of the tube here. And it's written as -2 over R, where R is the radius of our tube, times the surface tension of the liquid, times cosinus theta, the contact angle. At equilibrium, we have that delta P is equal to, we have a 0 pressure, and then the liquid will flow up and stop when the capillary pressure drop is equal to the pressure drop due to gravity. And that's why when you have these examples of fluid in tubes that are narrowing as you go to the right, you see that the little, very tiny tube has a very high equilibrium position as compared to the other tubes. And based on knowing all these, you can actually evaluate what is the surface tension, for example, or at least the gamma LV cos theta of your fluid. Now, in a porous medium, it's more complicated, and we have a porous body, And there, the delta P gamma is again written in the same way, except that instead of this 2 over R, we have SF, which is the interface area per volume of resin, which really represents what is the amount of available surface that we have in a given volume of our composite. Surface tension of liquids is typically low in this composite world because we used thermoplastics that have very low surface tension in the range of 0.02 Newton per meter. And then we have also even polyamides, which are a bit more polar, have a surface tension that is quite low. And epoxy is also in that range. So we are in a very low range as compared, for example, to molten metals or molten ceramics. So this is a reason why capillary pressure has been neglected in many cases in composite processing, because the values of surface tension being low, whatever the contact angle, the capillary pressure is also low. Another interesting aspect, which I always need to put, is if you look at Tintin, you know, the Capitaine Haddock, he also has to worry about surface tension effects when he tries to drink his favorite drink when on the moon. So now, for a very simple example for a composite, what do we have? Because we have this difference of scales between the channels and the toes. If I take channels of a given radius and I assume that I have a Poiseuille flow in the channel and I have a capillary driven plus pressure flow with a certain permeability in the toes, that we have a certain applied pressure at the bottom, let's say 1 bar, for example, we can evaluate the ratio very easily between the velocity in the gap and the velocity in the toe. If we do this, we will find that, this is a very small example I did playing recently with that. You can play with all the parameters and see what is this ratio of velocity in the gap and the toe will be when it's equal to 1. We have the perfect case where all the flow in the toe and in the gaps are equilibrated. So this is the limit of equal to 1 here. And we see that if we're below, we have capillary effects dominating. If we're above, hydrodynamic effects dominate. And we can play on for different conditions of capillary pressure, permeability of the toe, applied pressure, and see in which range we are, and try to evaluate then what would be the best capillary number or the best velocity that we need to be in that range. And it's quite interesting to see that depending, of course, on the channel radius, here they are very small. We also, depending, of course, on the capillary pressure we have in the toes, we can move this capillary dominated and hydrodynamic dominated space. And this is very, of course, crude, and many people have worked on many other molds that are a bit more advanced than this, but it points out some of the key features and issues. So what is the flow at the boundary between the toes and the channels? Of course, this will have, now I assume everything is going straight, but there, this flow here might also pour out here. And we see it in this case, which is a picture we took from a long time ago in the lab with a student, that we have the flow front driven ahead of in the fiber bundles, ahead of the flow front. The global flow front was here, and we see clearly that there is some effect here of flow going maybe across. The other question is, what is the role of transverse threads? So when we have transverse threads, we have they appear here, for example, they will actually block the flow, and they will also let, because we have wicking also in this direction, they will let at this time the flow go across. And so we have to take this into account as well. And then what is the capillary pressure in the toes? I assume the constant value. Of course, it's not constant with fluid velocity. It will change, and it's very difficult to determine. So there's following this approach of looking really what happens at the local scale. There are many papers that you can find in the literature trying to model this and understand, you know, by modeling what is the saturated flow here, what is the flow in the toes, how is flow going across, taking some boundary condition of coupling at the interface between the flow here and the flow, Darcy's flow in the toes. You need to know the microstructure, you need to know a lot of parameters, but if you can identify them, it provides good qualitative solutions in very limited cases of kind of model porous medium. But and that has been used and shows that we have something at least we can understand what we see based on these models. Now, there's another approach which has been taken by our colleagues in soil science, which is to say, okay, this is the local approach. What if we take it from the other side, the macroscopic approach? Because what we have is a porous medium, macroscopic, and we can measure what's happening at the macroscopic scale and maybe back calculate what's happening at the microscopic scale, but in a volume average method, if you want. So what you can do in this case is to look at the flow front. This is a very one that I took from my PhD thesis already, so it's a memory lane. But you have a pressure gradient, which is if you have a non-compressible fluid, the pressure gradient is constant. And then you have here a possibility that there is a sharp flow front and that you have a pressure boundary condition here, because if all the capillary forces act exactly at this line here, which is moving, then you have the capillary pressure drop, delta P gamma, that is exactly taking place at this location. Of course, when we do normal, when we do flow, we see that in most of the time we have an unsaturated zone here, and if you measure the pressure, we know that the pressure is in fact not so sharp, but it follows and it will go gradually. So this means that we need to take then some other aspects. For example, slug. So we have two methods. Either we assume that we have this perfect flow front here, which we would call a sharp flow front or slug flow, or we assume that we have a progressive saturation. And then we need to solve this to take into account the fact that we have porosity also in this region and a mix between liquid, fluid, and solid. And then we call it a multi-phase flow approach. So do we have spontaneous wetting in composite processing? That's the first question, because I showed that we have wetting in tube. Now we can do measurements, and there are also quite a few measurements like this that are reported in the literature. What is the case here is that we have a fabric. We put this fabric into a bath of liquid. In this case, it's water. And then we record where is the flow front versus time. So now this is, I hope you can see it because it's not always easy to see. We have the flow front here in this case, and the flow front is here in this case. And then the flow front now is here, and this case is here. These are the two same fabrics, twill, glass, the same fluid, distilled water, same experimental condition, same day, same temperature, same everything. What is different between these two cases? Well, if you were in my class, I would wait and ask you to give me some ideas, but since I don't hear you, I will tell you. And the difference is, if I can get my slides to move, that's always the problem with this laser pointer. Hold on here. Is that what we did on one of the fabrics is to do a corona pen treatment. So looking at the contact angles here in the pristine fabric, which is the normal glass fabric, we had a contact angle which is quite large. You see that the beads are a bit big here. And then when we treated with this corona pen, which is a plasma treatment, we have this treated fiber here, and we see the contact angle is much smaller. And as a result, we didn't change anything except the surface interaction between the liquid and the solid. And we clearly see that the pristine fabric has a flow front progression here, which is quite slow. And if we compare it with the treated fabric, we have a much faster flow progression. And we also looked at the treated fabric after some time to see if it retains. And if we analyze this, we can actually back calculate from there what is the capillary pressure, this apparent capillary pressure. And we have very low values in this case. We have a minus 0.33. If it's negative, it wets, so it's wetting, kilopascal for the pristine fabric, and minus 1.12 kilopascal. So it's a fourfold increment on a very small value. Now, are these values realistic? Can they be used in a pressure-driven experiment? The answer is no, I'm sorry, but the fluid at the flow front has a given velocity, and the contact angle varies with the local velocity. Again, if we look from the 70s, many people have looked at the flow in a capillary tube and then forced flow in a capillary tube with a given velocity and a given capillary number. And we see that the dynamic contact angle is actually, of course, not following exactly the static one, which you have here as the boundary condition at almost zero velocity, but that it increases such that the contact angle to the power of 3 is more or less linear with the capillary number. So there are many more models of dynamic wetting that have been developed since then, which are more advanced, but to give you a basic idea, this is already a pretty good model that we can use. And so we need to characterize the flow in the dynamic conditions during infiltration to estimate the capillary pressure drop value. Of course, we can do a forced capillary flow, but then what is a forced capillary flow? It's an impregnation experiment. So in that case, we can do it, we can model it using usual homogenization techniques with fibers and pores and liquid on a representative volume element. And then I go fast here because you all have courses, Professor Byron Pipes told me on Darcy's law, that if you take a very simple case of flow front progression in a UD, saturated, isothermal, non-compressible fluid, and so on, you have to write the mass conservation, the momentum conservation, which is Darcy's law, and you can solve the solution to find the position versus time. And the position of the flow front versus time is, in fact, such that L square goes with the T. So it goes, the position goes as square root of time. And then this corresponding coefficient here is a function of the permeability, viscosity, and volume fraction, and of delta P. And what is delta P? Delta P is the applied pressure difference. So it's the pressure that you have at the flow front here minus the applied pressure. So now, of course, the problem is what's happening. You have something here. Do you have what pressure do you take? Do you take the atmospheric pressure? That's what a lot of people do. Or should you take another pressure, which could be a delta P gamma, so this capillary pressure. So we can do this, and then we can solve it, having this delta P gamma here. In all rigor, the capillary pressure drop also depends on the fluid velocity, because cosinus theta depends on the fluid velocity. So we don't know its value. And so that's one reason why most people have been neglecting this, because if we take the equilibrium value, you're not sure you're taking the right value. Nobody knows. And we can measure it in a flow experiment. So that's what we did in the lab quite some time ago already. We measured using constant flow rate injection. We measure, in this case, you solve for a constant flow rate. So it's very easy to solve. You have this equation here, which says that the pressure at the inlet will increase gradually as time goes by. And so it's something that does not depend on the delta P gamma, and then something that is here, the delta P gamma. So if you plot the pressure at the inlet as a function of time, you should get the value of delta P gamma as an outlet for one given experiment. We did this, and of course, you have to have a lot of faith in what you do here, because you see a wiggly curve, that is a bit strange. But you can see that you can take the intercept between what you measure during most of the flow and the zero here, and you say that you have a delta P, and this is your capillary pressure drop. And we see in this present case that the positive delta P gamma shows that the flow is actually slowed down. So the faster you want to go, the more the flow is slowed down by these capillary effects, which in the end act against the flow. And we did this for many different experiments with different velocities of the fluid, because we had an imposed flow rate. And we plotted the capillary pressure drop that we measured from this as a function of the capillary number for all our experiments. And then we saw that indeed we have some changes. And we also saw that in that case, it was for epoxy and carbon fibers. If we plot the Tanner's law that I mentioned, this laws that says that the contact angle to the cube is proportional to the capillary number, we can then insert this into this equation and say that the capillary pressure drop will go as the cosinus of the cubic cube of the capillary number. And it works quite well. And we see also that if we go very slowly, we have something that wets. If we go too fast, in this case, the capillary numbers are quite high. We have a flow that doesn't wet, and we should be around here at some kind of optimal, maybe capillary number for that case. So this shows you that we can actually extract the capillary number from this. Now, I just mentioned before that there is another place where we see the capillary numbers and we can actually measure them, is when we do a permeability measurement. So if you all do permeability measurements, you plot the flow front position versus time. This is again stolen from Joël Bréa. And then you evaluate the L square over T, and then you know the viscosity of your fluid. It's a model fluid that you take, and you evaluate the permeability. And you find this value, and then you have this. Just a small point is that permeability, in any case, is not easy to measure. And we've been participating in round robins of permeability measurements over these past many years. And this is just to show you that I like to show this to my students as well, because this was in 2000, so it was published in 2011, it was a bit before. They gave fabrics to 11 groups or over the world. We all had to measure the permeability, and this is what we came up with. You see there's a big difference in values. And then they say, no, but we have to redo a second. And then we use the same fabric, but we have to use the same fluid, silicone oil. We follow the same precise guidelines. And we all came more or less into the same value, plus or minus 21%, which is still quite high, but except those who did not want to follow the recommendation. And we said, okay, follow the recommendation and you will have the permeability value. Of course, are those values correct? We all have the same value, but are we all wrong? And is the real value here? This is something that we still, at this age, don't know. So what we can do is to do a non-saturated permeability measurement, as we just showed, with a well-known fluid, and then do a saturated permeability measurement, which you do by simply measuring the flow. So it's the Q, the volumetric flow rate that comes out, and you weigh the weight, for example, of the liquid that comes out on the scale, and you can very easily find what is the saturated permeability. This one does not depend at all on capillary effects, because the saturated means that all the fluid has gone through, come out, there is no air, no nothing, and so you don't have to worry at all about capillary effects in this case. We see that K sat and K unsat are often not equal, because if you do the measurement of K unsat, what you take for delta P is very important. And typically you will say, well, it's the fluid pressure at the inlet, I neglect maybe there's maybe pressure in the air, okay, I take this into account, but I forget about capillary pressure. So we redid the calculation, and we're not the only ones, because it's been done also before, is to say, well, if we compare those two, we can actually solve the solution of this delta P, but in one case, we do it the way most people do, is to say, oh, we call it K unsat, it's measured, measuring the flow front, but we take this delta P, which is the pressure we apply here. Or we can say, no, in fact, the permeability that we measure is the saturated permeability, but the pressure boundary here at the flow front is not K unsat, but it's delta P applied minus P in the gas, but it's delta P applied plus this delta P gamma, which can be positive in the case where it doesn't wet, or negative in the case where it wets. And so if we then compare these two, we have K unsat over K sat, there are these two values here. We see that they actually are linked by 1 plus delta P gamma, the capillary pressure drop, divided by this delta P. And so if this ratio is below 1, we are non-wetting. If it's above 1, we have a wetting case. So this RS is a good measure of the capillary pressure drop. But K unsat is a priori not a good measure of the permeability, depending on the test fluid and test conditions. So we took our corona-treated fabrics and we did permeability measurements on these with the pristine fabrics, K sat and K unsat. With the treated fabrics, K sat, K unsat, we see that, okay, we have the trend that everybody sees, we change with volume fraction. And if we plot the ratio of the permeabilities, we see something very interesting, as we expected. For the pristine fabrics, we see that the ratio is below 1, which means that they are not wetting that well. But with the treated fabrics here, we see that the ratio is above 1, which means that they are wetting. And if we extract the delta P gamma very simply from this ratio, we see that the capillary pressure drop that we measure here is negative in the case of the treated fabric. And the more volume fraction we put, the more negative it becomes, because the more capillary effects we will see. And if it's not treated, we see a bit of this effect, but still we see that it's not really wetting very much, but it's close to 1. Okay. So it's a very simple way to approach capillary pressure measurements. This can be used also in extreme cases, and this is an example we did recently in collaboration with friends at Leuven and MIT, where we tested the permeability of CNT grafted fabrics. So these were alumina fabrics. They grafted carbon nanotubes on the alumina with different lengths, different structures. And then we tried to measure the permeability, which was difficult due to the size of the fabrics as well. But we realized that in this case, we have a ratio that is very different whether we have the CNT or not on the fabric. And it goes from 0.8 to up to almost 2. So this is an interesting effect. We can also compare between fabrics, glass fabrics that were supplied by Chaumarin in France. They are developed to increase the permeability, and they have toes with a very large gap in between, as compared to normal plain weave, or these are not plain weaves, twill weaves actually, that we could use also. The microstructure is very different. As you see here, we have a lot of very big gaps, whereas in this case, we have not so many big gaps. And when we measure the permeability, we see that in one case, we have what we wanted, a very high permeability. In the other case, we have the normal permeability. But if we look at K sat over K unsat, so again, this ratio with different fluids for which we know the density, the surface tension, and so on, we can find a range of analysis, because in this case, we had also constant pressure instead of constant flow rate. So we found a place where we have a more or less constant capillary number here. And we did the analysis, and we find that indeed, if we go very slowly, we have capillary effects that dominate. If we go very fast, we have, in fact, a permeability ratio that remains always close to 1, in particular in the case of this G black. And we were wondering, like, why is it always equal to 1? And if you're interested, you can read our paper. But the main reason is that, well, capillary permeability in this case is dominated by the presence of these huge gaps. And so we don't care so much about the toes because they are almost inexistent. And if we look at the flow front, we see that for very low capillary numbers, we have a more or less uniform. But if we have a high capillary number, the saturated flow is here. And here we have a lot of dry toes that we can see. And which means that you have to be careful, because if you actually stop the flow when you have liquid that comes out here, you stop, but this is not impregnated at all. We just have basically channels. So this is also a limitation for the development of the new fabrics. And what is the effect of this unsaturated zone on composites? It's something that leads us to say, well, maybe we should take a closer look to what we see at the dual scale very closely on the fabric. And depending on the, here it's driven by capillary forces, you can see it, here it's driven by viscous forces. We also see little bubbles that remain here. And how to get snapshots of these, and are dynamic measurements of saturation possible to see. And I have to speed up because I see that I've been talking too fast, too much. We can see them if we stop the flow, which is always a dream that I had. And we managed to do it using UV curable resins. So you see the flow front, and then you snap it and it stops. So with very fast curing resins, we can stop the flow front and look at it. And then we can take pictures. We can also go to the more advanced techniques like tomography. And here we can see that in the pristine case and treated case, again, our two fabrics, if we have an intermediate capillary number, we're in the case where the flow front is more or less equivalent. So we have here, it's more or less flat. In the case where we go too fast, flow is driven in between, and we see that flow lags behind here. And if we go too slowly. It's a bit more difficult to see here, but there is a zone here where we have a flow lagging behind. So we can see them a bit better here. So, of course, there are many methods, and again, in the literature, you can find a lot of papers. There are some colleagues in Canada have looked at using visible light transmission and some fluorescent dyes. Now, with the advent of tomography, especially very high synchrotron source tomography, you can really look at the impregnation of a single toe. There's a very nice paper done by our colleagues from Spain, but it's 120 minutes per scan, so it's very slow flow. And then there are some other examples of using MRI imaging during impregnation, but again, a very long scan time. So we try to find if there is a way to improve this and find a kind of an intermediate, something that will allow us to look through, but at the same time, that is also not too slow. And recently, we've been working with the CSAM in Switzerland on fast X-ray methods. So this is a X-ray source, lab scale. We have a detector and we have a sample. That's the traditional way of doing it. But in this case, we use phase contrast imaging using interferometric elements here, which are placed here, different gratings, which will create interference patterns. And then by doing a phase stepping, you can actually extract a lot more information than you can with the normal absorption image. In particular, if you have a carbon fabric and just a normal carbon fabric with fluid, there is no difference in the absorption and you don't see anything really interesting. If you look at the refraction, you see a bit, but not so great. But if you look at the scattering image here, you start to see your carbon becomes clear and the infiltrated region becomes very obvious, and you can see the flow patterns very well, and you can see them here live. So using this technique, we also saw that, of course, there are some limitations, especially in the capillary dominated flow, where the fringes are a bit difficult to see. And again, you need a lot of faith and a lot of image analysis to be able to extract something. So we can also play with contrasting agents, as people do normally in tomography, and use conventional absorption images. That's what we did here. So you see in absorption mode here, we don't see very well the difference, but with the Zn iodine contrasting agent, we see a very good difference in the absorption image. And in the scattering image, we see a bit also, but here the absorption image work quite well. And so now we can compare capillary dominated flow. Oops, and I have to again go to the automatic. So these guys here are capillary dominated flow, which I will go faster here. We can see here the balanced flow. And then we can see here on this side, the viscous dominated flow. And so if we compare them all, we see that we can get snapshots. One image takes about 8 seconds. So it's not perfect, but it's already much better than 120 minutes. And we can really image realistic flow. Also, there's no limitation. You can use epoxy resin. You can use whatever resin that you want. So, and then, of course, you can get the saturation curves from the grayscale analysis. And you have saturations every 9 seconds, so every scan. And you can then extract saturation versus fabric length. With this, you can make saturation curves. And then you can use this to calculate what is the zone that is here not fully impregnated. What we see in this case, if we normalize this saturation as a function of Z over time divided by the imposed velocity, so it's 1. If it was a complete slug flow, we would have something that goes completely here and goes down to this 1 curve. We see that depending on the cases, we can extract different saturation curves, different behavior. We confirm that the intermediate, more or less balanced flow has the steepest curve here, but we can also extract a lot of data from this. And this is ongoing. And now I showed you something that we did before, but using not so nice data, but data that was taken from visual aspects, we can back calculate saturation as a function of pressure. And if you know this saturation as a function of pressure, for different cases of imposed velocity, you can plug them into the equations and you can really solve what is the non-saturated flow using a multi-phase flow approach, back to soil science methods. After flow ceases, you see, and I need to speed up because I see that I'm a bit over time. So you have the capillary dominated flow, balanced flow. You see the porosity present here. So you can also analyze the data for porosity and movement of fluids. Natural fibers are also a very interesting case, which also works with this system, because in this case, the fibers remove liquid from the main stain, they absorb liquid, and they can swell. So they will change the permeability. And this, we've also observed this in twill fabrics, for example, that are, or flax, sorry, that are UD or twill. And we see different cases, and we can actually observe that the space here, non-saturated space, is different and changes as the flow progresses, even though it's with an imposed flow rate. So it should be the same all over, and that's what we see with the color. So, and for those who don't like black and white pictures, we also can use some tricks to better image what is the flow front by playing on this level, and then we can really do a lot of tricks with the imaging analysis of this. So I will conclude and to say that I hope you're convinced in liquid composite molding processes, capillary effects take place close to the flow front. They may affect the flow kinetics and the part quality. Unsaturated and saturated permeability measurements are useful to be combined to provide indication on capillary effects. And you can also work on permeability enhancement, but of course at the cost of increased dual scale flow. The optimal capillary number, I don't reveal any value yet, but it's strongly linked to the dual scale dimension and to the fluid interface properties, of course. But these new observation methods that we are developing, and many others are also developing, help elucidating the link between the surface tension effect and the pore geometry, as well as the time-dependent effects. And this is hopefully something that will help us to many perspectives by introducing better dynamic wetting models, by introducing the effects of the viscosity, because if you take a thermoplastic, you will also have molecular arrangement effects, which also take place during flow. And of course, the bubble transfer, diffusion, and collapse, and improve the models that allow us to predict basically, will we have porosity and can we do it, but without having to go very slow and to go at decent speeds. So with this, I would like to thank you all, and I have particular thanks to give to, of course, my colleagues of the lab. Here, as you see, we are on the top of the world in Switzerland. We do ski outings, and I have to thank Baris, who was a postdoc in our lab and is now a professor in TU Delft. Elena, she's here, Elena, and Valentin is here. Hirun, Elena and Hirun are PhD students. Valentin is a postdoc in our lab. And also Damiano Salvatori, who did a lot of work. And also support, of course, from EPFL, from the Swiss National Foundation, from the Swiss Competence Center for Energy Research, and the European Community for funding various aspects of this research over the years. And I have to thank by saying, of course, that you're welcome to come and visit us in Lausanne. Not to talk so much about capillary effects, but about composite meat sustainability, but there will be a lot of discussions on capillary effects, I hope, also then. Thank you.
Thank you very much, Professor Michaud. I'm Jonathan Goodsell. I'll be handling questions. And just a reminder to please enter your questions into the Q&A box. I see we have a number here. And if there's questions that we don't get to in the time today, we'll post those up. We'll send those along to Professor Michaud, and she can respond as she is able. And a reminder, this, of course, will be all kept on cdmhub.org. So let me begin with a question that was that inspired by the last piece of your work with natural materials. And someone asked the question, how can we work towards accounting for the natural variability in materials when we're using these capillary effects methods?
That's a good question. I mean, the natural variability of, especially of natural fibers is intrinsic. And what we can do is at least observe them. They have also interesting capillary effects, these natural fibers, because they're hollow, there are all kinds of interaction with the fluids. And if we, I mean, it's difficult to say how to counter this. The only way we can do is to accept that there will be variability and to try to take this into account in the design and into account, of course, in the prediction of the velocity and so on. And maybe use our techniques to give the bounds and to say, okay, with these different flax fibers, for example, from different years or different treatments or different this and different that, we will how to treat the fibers to get minimize these differences is one point, and also what are the differences. And we know that maybe we will predict the flow kinetics plus or minus 5%, but at least we know it and we can be conservative when we do our parts. Same for the mechanical properties, actually, for these fibers.
We have a couple of questions that all revolve around a similar theme, which is deformed fabrics, in the case of whether it's curvilinearly deformed or deformed in the manufacturing process, or even some maybe 3D woven fabrics and otherwise, and how to account for these capillary effects in those conditions.
At this stage, we haven't done deformed fabrics. We're already looking at non-deformed fabrics. If you know how they're deformed by draping, you know, there's a lot of very good work done on simulation of draping, and you know what is the local variation in the aspect, the morphology of your fabric. And if you are able to predict, knowing the morphology of the fabric, what the capillary effects will be, then you can actually introduce this into your draping model, because you know what is how is the size, the gap channel changing if you compress it locally or if you shear it locally, how is the volume fraction in the toes changing. So this is the next step. We're not there yet, but there's no reason why it should not be introduced into these draping models. So.
Thank you. There's a question around how can you use these findings to tell whether a given fiber and resin are compatible or not for liquid molding?
Well, you can use it to, how to say that? What you can do is a bit what we did. I mean, being compatible means what? Means having good interfacial properties and they don't delaminate when you do a mechanical test. In this case, you would like to have a strong bond forming typically, or maybe less strong bond, depending if you want impact absorption. But and then you can tailor this interface. And then typically that's what drives. And then we're working on the processing are a bit like the pore, trying to make sure that we can process what the properties dictate that we need. But most of the time, then you can play a bit by activating the surface, like we showed with the corona treatment. If you need to enhance a bit the capillary effects, most of the time it's also could be. I think the effect of the surface is important, but it's also the effect of the pore network that is important. So if you want to increase the capillary effects, you can add some elements, or you can treat the surface, or you can avoid to have large channels, for example, in your fabric. So it's really a design of the fabric versus the mechanical properties that you need at the end. So there's no simple answer. We can use it at least to measure and to see if we need to tweak a bit the sizing of the fibers or the treatment of the fibers, or or we need to compress it a bit more to favor these effects or not favor them. There's no simple answer.
all the good questions have no simple answer. Let me throw one more at you, and it also has no simple answer. It's, what is the next game changer idea in liquid molding of composites?
Wow. I will not tell you. No. I don't know if there is any game changer ideas. I mean, ideally, there are a lot of things going on in the development of new resins that cure without too much heat and too much pressure, using UV or using frontal polymerization. So I think in the chemistry of the resins, there is still some work to do. I I'm pretty sure. Also in terms of sustainability, another game changer that I think is important, but I don't have the solution for that, is how to make our liquid composite molding processes a bit cleaner in terms of all the consumables that we need, all the demolding agents, all the vacuum bags, and all this sealing, and I think that's something also that we need to work on. So for me, the game changer maybe is to make them more energy efficient and less impacting. That's one idea, but otherwise, of course, I think there's nothing really to do. It's the process is a very simple one, and it's a physics of just pouring liquid into a porous medium. So.
Thank you for that, and thank you for this very engaging talk. We're here at the end of our hour, and I am sharing the wrong screen, so I'll try to share the right one here real quick as we wrap that one up. And thank everyone for their time here and their attention. And again, thank you, Professor Michaud, for this very interesting talk. More questions can be asked on CDM Hub. We'll post this there. There have been a number of people asking. This will be posted on cdmhub.org, and we'll send you an email with that link once it's up. And invite all of you to join us again in 2 weeks when we hear Professor Francois Truchot talk more about liquid composite molding. So with that, I'll wish everyone a good day, and thank you all very much.
Thank you.